Welcome to Spring LIB.
We have a pendulum bob here. So we have the string. Again, we're going to assume that that's weightless. And it's initially in a position that looks like this. And I'm assuming that we're measuring theta from here. Not sure why I drew it this way. Probably should have drawn it this way. But anyway, it's symmetric. So we're measuring theta from the negative x-axis clockwise. So, um, so we're asked when theta equals 0, what is the tension in the cable, in the cord? Well, that is, we draw a free body diagram of the bob in that position, and we can see that we have the weight here, and that's causing we have acceleration in the, let's see here, we should actually maybe put that in, an acceleration in the vertical direction, because remember the acceleration always has to be tangent to the cord. And so that means that there's no acceleration in the horizontal direction, which means that the force has to be 0. So F equals ma in this horizontal direction says that t is 0. And we could also figure out what the acceleration is, and that's just going to be g at that point, right? So we can then they ask us for what do they ask us for? What is the tension, and also the instant the bob reaches the tension when the bob reaches 45 degrees. Okay, so down here, or we could have said down here. Either way, it's going to have the same tension. So we draw a free body diagram of our bob, and we know that now the acceleration vector is tangent. The velocity vector is tangent to this point, and then we get the acceleration is so there's a component of acceleration in the radial direction and also in the tangential direction. So again, up here we only had a component in the tangential direction. Now let's see here. We can then take this and draw a free body diagram, and again do our force balances. So we know that I'm going to do a force balance along this direction and then along this direction. So in this direction we have T. I'm going to assume this is positive. And then we have a component of W here, the weight, in that direction. That's this, but it's in the opposite direction as T. That equals the mass times the acceleration, the radial acceleration at that point. And the radial acceleration is the mass times is the centripetal acceleration, v theta squared over r. And in the tangential direction here, we have the tangential component of the weight, and that equals the mass times the acceleration in the tangential direction. Now we have what we don't know is we don't know this, so we need to figure out what this velocity is, and so that is the total velocity of the particle, of the bob, and so we can, because there's no velocity in this direction, and so we can use conservation of energy to figure that out. So we know that if we measure energy as our datum from up here, we've lost some potential energy and we've gained some kinetic energy, and that has to be 0 since we had the velocity at this point was 0. So we have, and I guess we're told that, again, I guess I should actually make sure that we actually write this down, that the velocity, let's see here, velocity is 0 here. Okay, so that's it's released from rest. So we had 0 energy here since we use this as our potential energy datum. So that the potential energy plus the kinetic energy has to be 0 at all points on this path. So this allows us to solve for v theta in terms of G, R, and the angle here. So we know all these things. We can plug it in and we get 11.7 meters per second. We could also just take this equation. Okay, we can solve here for t. We actually don't need this for this problem. We could figure out the acceleration in the tangential direction if we wanted to. So we can solve for t, and so we get that t prime, oh, this is t prime, this is the tension down here, is the mass times the centripetal acceleration plus the weight times sine of theta. Now we can actually just plug this into here, and then lots of things cancel out, and this term just becomes 2 times the weight times sine of theta, and then we have plus another weight times sine of theta. So in fact, at this point, we just have 3 times the weight times sine of theta, and so all we really needed to know, they told us what r was, but we can see that in fact r doesn't matter in this problem, and we could have figured out this tension without that knowledge. And that turns out to be 10.6 pound force.